we will slowly begin our talk. So it's a pleasure to have Thomas Icard from Stanford University here. And Thomas visited Moscow a long time ago when he was still a student in Amsterdam. And since then, as they say, a lot of water has been shed. So to say. But now a professor at Stanford University will speak about logical foundation of causal inference. Please.
Great. Thank you so much. And thank you so much for having me here to speak. It's really a pleasure and an honor to be speaking in the seminar. As Professor Kamyshev just mentioned, my very first serious research project was carried out under his generous guidance a little over a decade ago there at Stikloff Institute, and this was a completely formative experience for me. So it's really meaningful to be presenting in this seminar. I've also, with great interest, followed lots of the other work over the last decade from the larger Moscow group, which has all been really inspiring and fascinating. So over the last decade or so, I've pursued various interests in philosophy and some more empirically oriented kind of research areas like AI and cognitive science. But I'm very pleased that just pursuing interests where they lead has brought me right back to some of the very same themes that I was introduced to by Professor Kamyshev, namely connections between logic and arithmetic and also topology. So the angle here is going to be slightly different from some of the work on modal logic and topology and provability logic, but some of the very same themes will actually show up, just a little bit different of an angle. So the high level kind of point that I want to convince you of is that there's this sort of two-way street between causal inference, these kind of empirical issues about how do we infer causal quantities from different kinds of data, and for that on the one hand and logic on the other. So if there's one kind of takeaway from the whole talk that I hope you'll remember, it's this one picture, this one slide, which is that we can actually understand much of what people are up to in the field of causal inference as involving the following kind of problem. If I'm given some assumptions, or let's say I'm given some type of data, and I am willing to make certain kinds of assumptions, when do those data together with those assumptions imply or entail a causal conclusion? So people in the literature don't usually put it exactly this way, but I claim, and I'm not going to argue for that claim here, but most of what people are doing in the field of causal inference can actually be understood in this way. And much of what people are up to there is, to the extent that it's formalized, is formalized kind of model theoretically. So we're dealing with causal structures and assumptions on causal structures and different kinds of data, and then asking questions about what's guaranteed by those assumptions and that type of data. And one move that I want to make in this talk is to essentially turn this into an actual entailment problem for a formal language. So what kinds of formal languages would make sense for encoding assumptions, asking causal queries or causal conclusion type questions, and also formalizing data, the kind of data that you might get, at least in an idealized sense. So this is the sort of high level picture that's going to be motivating much of what I want to do in the talk. And specifically, the plan is as follows. I want to give some background on causal models. I'm not going to assume that people have seen these before, so-called structural causal models. And then I want to introduce this hierarchy of formal languages, of logical languages. And these are going to be essentially probability logical languages for reasoning about causality, reasoning about these models. So we kind of bring in logic already from the get-go there. And then I want to ask some of the standard questions that I think are nonetheless interesting in this setting, namely questions about axiomatization, computational complexity. And then I want to bring in topology. in a kind of in a big way. And I want to topologize these causal models, and that's going to establish a kind of bridge, kind of concrete bridge between the work in logic and more empirically oriented questions about causality. And the main result there is the so-called causal hierarchy theorem. So that's my plan. I'm not quite sure how long all of this will take, but you can stop me or tell me to speed up or slow down whenever it makes sense. And I also, you know, I know that sometimes you will ask questions in the middle of these seminars, and I'm very happy for that. So if you want to interrupt with clarification, or even if it's not clarification, it's okay with me. I'm happy for this to be more of a discussion. But as you all see fit, it's great with me.
Yes, we like to interrupt the speaker.
Fabulous. That's wonderful. Interruptions, welcome. Okay, so background of causal models. So, you know, when we're thinking about this through the lens of logic, we're going to be thinking of these things as, you know, the model theoretic objects that we'll be eventually dealing with. But these actually come from, you know, these are essentially as defined in the causal literature. So a structure or a model is given by 4 components. First of all, these 2 sets of variables, endogenous variables and exogenous variables. And the signature here is assumed to be fixed. So each of these variables has a given range of values that it could take on. And the endogenous variables are the ones that we essentially are going to want to be reasoning about or interacting with in some way. So the kinds of variables that we might observe, the kinds of variables that we might be querying, we might want to ask about, or that we might want to be changing by some action on our part. They're the variables that we're interacting with in direct ways. But when we're dealing with causal setups, there might also be sources of exogenous variation. And these are the exogenous variables that maybe affect the endogenous variables that we care about, but we're not directly measuring them or asking questions about them or changing them. They're present, but we have no real access to them. And those are 2 different kinds of variables. And each of the endogenous variables comes with a so-called structural function. So this is a function for the variable x that determines its value as a function of the values of some other variables. So f will take as an argument the values of some set of other variables. Those are usually called the parents of x, the causal parents of x. And so if I know the values of those variables, then I know the value of x. And this function determines what that value is. And often we will make further assumptions about these structural functions. For instance, if I trace the dependence of x on y, on z, and so on, I have no cycles. So x doesn't causally depend on itself is often a plausible assumption that we'll want to make about a causal setup. And so that's the first 3 components, the endogenous variables, exogenous variables, and structural functions, 1 for each endogenous variable. And finally, we have a probability distribution on the settings of the exogenous variables. So this is can be totally general. It could be any probability distribution on the exogenous variables. And that's what a structural causal model is. It has these 4 components. So I want to give a couple of examples, somewhat simple examples, sort of toy examples, but nonetheless sufficient to show what these look like. Here's an extremely simple example where I have 2 endogenous and 2 exogenous variables.
And may I interrupt with the
Of
question?
course.
So this set F of structural functions.
Yes.
So these functions, what are they domain and range? So what are
Yeah. Good. In the totally general case, the domain is the vector of values of all variables other than x. Mm-hmm. And its range are the values of x. So each variable comes. I haven't written this down in the signature here, but each has its own range of values. In the talk, they'll mostly be binary, but they could be arbitrary. So these, as a simple case, they could be all 0, 1, and so it takes as argument the values of all the other variables, and then gives me a value for this variable x. But the assumption that I mentioned, where we have acyclicity of dependence, means that we might have just a restricted set of variables that x depends on. maybe it just depends on y and z, and y doesn't in turn depend on x. So its domain can be restricted and usually will be restricted. Yeah, thanks for the question. So here's a simple example. I haven't written out the function. I've just written out the function as a kind of assignment, so that we have two exogenous variables that are just fair coin flips, essentially Bernoulli 0.5 probabilities, and x is just a function of u1, and y is just a function of u2, and it's actually just identity function. So x just takes on whatever the value of u1 was, and y takes on whatever the value of u2 was. And we can draw the dependence structure like this, the qualitative dependence structure, where y depends on the first exogenous variable, x depends on the second, or vice versa. Okay, so we could also have a slightly more complex situation where now y depends not just on u2, but it also depends on x. So this is a case where I'm assuming everything is binary. So we can just write out the functions as Boolean formulas, and x again just takes on value u1, but now y takes on value 1 if x and u2 are the same, 0 otherwise. And so now y depends on both of these variables, an endogenous and an exogenous variable. Okay, a slightly more complex example. Here's the type of thing that you might want to be able to model with these, a little medical scenario where we have now 3 endogenous variables and 4 exogenous variables. And we might think of x as something like whether a treatment is prescribed by a doctor, y is whether a patient survives, and z is the presence of a symptom. And then we could write out this model in the following way. Maybe z depends conjunctively on these 2 exogenous sources of variation, ur and uz. Maybe x, whether the treatment is prescribed depends on the presence of the symptom, but also, what kind of doctor you have, ux. Maybe ux is something like that. And so it's, going to be prescribed exactly when, the symptom is present if you have a certain kind of doctor, otherwise not. And then survival, y, might depend on, whether the treatment is given, and also this other exogenous variable ur, and maybe also its own source of variation uy that isn't impacting any other endogenous variables. This is somewhat of an arbitrary made-up example, but this is what this might look like. And then we could have some, again, all of the exogenous variables here are distributed independently. That need not be the case, but here they will be. And then the dependence structure here is slightly different. It says that, whether a treatment is prescribed by a doctor depends on ux, but also on the presence of the symptom. And then survival depends on whether the treatment is prescribed and also this source of variation uy. And then there's also this source of variation ur, which is exerting kind of force on both y and z. Okay, so this is not the kind of thing that a modeler or a data scientist would actually plausibly write down, but is an example of a hypothesis, a possible way that the world might be that we might, want to be making queries about, right? So we might want to ask various questions about the scenario, and we don't actually have access to this underlying ground truth, but we might want to know, can we learn anything about this underlying ground truth from, ways of interacting with the system like this? Okay, so these structural causal models should be understood from, the sort of scientific perspective as possible hypotheses about ways parts of the world might be. Okay, and this is a kind of mathematization of causal structure. Okay, so the first thing to note here is that by putting this probability distribution on the exogenous variables, those essentially filter through the functions to give rise to a probability distribution on the endogenous variables. So if we make some assumptions like the ones I mentioned, that functional dependencies are well-founded or acyclic, or assumptions of this sort, depending on the variable space, then you can show that a given exogenous setting uniquely determines an endogenous setting of all the variables. Okay, so what we do to determine this probability distribution on endogenous variables is essentially sum over all those exogenous settings that would produce this endogenous setting. So I want to know what's the probability that some variables y, and I'm going to be using here, by the way, bold, if it's clear that that's bold, bold y for a set of variables and set of values, little y. The probability of that tuple is given by the sum over the probabilities of the exogenous settings that would produce that endogenous setting. Okay, so in an example, if we go back to this example, I can compute, for instance, the conditional probability of y being 1 given that x equals 1, where we need to compute the probability of x and y both being 1, then divide by probability of x equals 1. And so we essentially sum over all those settings that give x and y both equal to 1, and then divide by the probabilities of the settings that give just x equals 1. Okay, and we can just compute that in this setting. I won't go through the calculation of this, but it happens to be 0.74. Okay, so the probability of, this says the probability of survival, if we actually observe that treatment was given, is 0.74, which is to say, whatever this scenario, doctors are doing a pretty good job, I suppose. Survival is relatively good when people are in fact prescribing treatment. Okay, but what makes these models distinctively causal? So far, they just look like probability models, but what makes them distinctively causal is that they also give rise to these other quantities called potential outcomes. So these are essentially intuitively kind of conditional statements, which will be written like this to say that we're going to be asking about the probability that y would equal y if conditionally speaking, x were to have values x. Okay, so this is a kind of conditional statement where we write x equals x in the subscript there. And if you're familiar with the philosophical logic, this is similar to counterfactual conditionals that people sometimes write that way. And sometimes this will also be written in a dynamic logic kind of way, such that we say, were x equal to x, then y would take on values y. And so these are so-called potential outcomes. And to assess the probabilities of those, we need to change our model essentially. So if we have a model M, a structural causal model M, we can intervene on that model to create a new model M with x equals x, where we essentially go in and we leave everything the same, except we change the functions for these variables x, and we set them to the corresponding values, little x. Okay, so we keep everything the same, except that we change the mechanisms, the functions, for those variables that we're supposed to intervene upon. So going back to this example, this is the model as it just works by itself. If I just let it run forward, so to speak, then we saw what some of those probabilities look like. But I can also go in and change it from the outside, so to say. And if I intervene to set x equal to 1, then everything remains the same. I just change the equation from whatever the default for x would have been as a function of z and ux. I change it to just be set to 1. Okay, so a fairly simple operation, but it now gives us a new model, and it gives us a new type of distribution. This is so-called interventional distribution, or what you might call an experimental distribution, which says, what is the probability of y having some value if I were to intervene on x? And so this is determined in exactly the same way as before, except that the model is slightly different. The functions are manipulated or intervened upon. And so to ask what's the probability that y would equal y, upon this intervention, I sum over all the exogenous settings again, but now I'm asking for this, for this new set of structural functions, I'm asking still for y equal to y. Y to be equal to y.
Thomas, may I ask?
Of course.
In this example, so do you, when you intervene, do you also force the previous value of x? I mean, because you had that x is z equivalent to, so this would imply that if x is 1, that z is actually equal to u of x. So
Great.
do you force this also?
Not at all. So that's
You're just free of this assumption.
Exactly. That's exactly the right question here, and that's what's going to make this different from conditioning. So so indeed, so I'm essentially overriding the mechanism, right? And now what's going to happen is that Z is still will be whatever it is. It's going to be drawn from UR and UZ, right? But X now is not dependent on any of those variables anymore. You essentially cut off the dependence of X from all these variables. That's exactly the right question. So oh, by the way, in the literature, sometimes you will see this written as probability of Y equals Y given do X. So it looks like conditional probability, but this do operator is there to distinguish it from conditioning. And so exactly as Momoko just asked, here's an example. So we just saw that the conditional probability of Y equals 1 given X equals 1 is 0.74. What happens if we go in and change the system? So imagine, I'm someone looking at the system from outside, and I see doctors prescribing medications in different combinations. And now I just say, I want to override whatever they would do and just set X equal to 1. So I just want to give the treatment. Then you see that if you recalculate the probability of Y, it drops to 0.25. Right? So the conditional probability is going to differ in a crucial way from the interventional probability, because we're actually perturbing the system. We're not letting it act according to its ordinary laws. We're kind of going in and changing it. Okay, I won't do this calculation, but we can walk through it if hopefully it's clear what you would need to do to get this number. Okay, so as a little interlude, I just want to mention that bringing in now logic already. This is not something that we're doing anew. This has been done for decades, actually. Bringing in a kind of little logical language for reasoning about these interventions. Suppose we bracket for the moment probability. So forget about probability for the moment and just, let's say, fix an exogenous setting. Just fix it once and for all, or consider it fixed. Then we can consider a little modal logic, a little conditional logic that has sort of two sorts of propositional formulas. Alpha are essentially the interventions, and we're just going to allow interventions to be essentially literals. So assuming everything is binary, I can either set a variable to be equal to 1 or 0, and I can do that in any combination. Then we take phi to be generalized grammar, where I can state that one of these variables has a given value, close under Booleans, but then we can also essentially assert that phi would be true under an intervention alpha. So this gives us a very small kind of modal language. And we can ask about its axiomatization, and this has actually been considered in the literature. And so I just want to mention it. It will actually come back later. This is back from Gallus and Pearl and Halpern, and we've also extended it recently to kind of infinitary setting. So what does it look like? You have Boolean reasoning. So again, this is fixing an exogenous setting. What's the sort of logic of this conditional, right? So it's basically a normal, the alpha interventions are kind of normal modal operators. Where we have a kind of necessitation, we have a success, number 3 here. It says if I intervene to set alpha, if I intervene to make alpha true, then alpha is true. Interventions are successful. We have K, and we also have that this commutes with negation. So the diamond in the box version kind of collapse into one modality. The distinctively causal parts of this are this number 6 here, which says that if I intervene to set alpha and then beta and gamma both result, then if I also just intervene to make alpha and beta in the first, then gamma still results. So I can sort of take a result and bring it into the intervention, and that doesn't change things. And finally, this last axiom, this will all be complete together. This last axiom is coming from the assumption of acyclicity. So what does this say? Each one of these statements that looks a little bit complicated here. Like the one that is my mouse visible if I am not really. Okay, so each one of these conjunctions essentially states that a variable xi causally impacts a variable xi plus 1. So suppose I have some list of variables x1 up to xk. Then the kind of antecedent of this big conditional says x1 impacts x2, x2 impacts x3, and so on. And then the very last statement here, the consequent says that xk can't also impact x1. Now, why does each one of these say that? Well, I'm taking xi to be the ith variable, and li plus 1 is either xi plus 1 or negation of xi plus 1. And then alpha I is any kind of context that would witness the influence. So what this says is that xi in some context would lead to, let's say, xi plus 1, but negating xi, so setting xi to 0, would lead to xi plus 1 being 0. So essentially toggling xi has an impact on xi plus 1 in some context alpha. And so if that's true from 1 up to k minus 1, then the very last one can't also be true. You can't have a cycle. Okay, so this essentially enforces in a kind of brute force way absence of causal cycles. Okay. And these principles are complete for the setting where you just fix an exogenous variable and you want to know what's the behavior of this conditional operator. Okay, so that's a little excursion into the purely deterministic setting. But now returning to the probabilistic setting, one of the things that we're often interested in science and engineering and philosophy and so on, it's not just these kind of hypothetical probability questions that we've been asking about, but also counterfactual distributions. So what's a counterfactual distribution? Well, this is, again, a quantity that's defined by any causal model like this, where I ask about the joint probability of a bunch of conditionals all holding at once. And in order to do this, I need to separately consider interventions on the model that are sort of potentially incompatible. So X and W might specify different interventions in the model. Maybe one is setting X equal to 1, one is setting X equal to 0. And I want to know the joint probability of these conditional statements being true, all under the same endogenous settings. So how does this get determined? And I'll say in a moment why we even call these counterfactual. But if I want to assess this probability, I, again, just sum over all the U's, probabilities of the U's. But each one of these U's must independently make each one of these conditional statements true. Okay, so that's the so-called counterfactual distribution, where I'm asking essentially the probability of a whole set of conditionals being true at once. Okay, so returning to this example, and I'm also, this is the medical scenario, same example. I'm gonna, for abbreviation, write lowercase y and lowercase x for y equals 1 and x equals 1, just because this will get notationally heavy if we keep writing y equals y. So we calculated these two before, but now we can also ask questions, not just what would the probability of y be if I set x equal to 1, but also, for instance, what would the probability of y be setting x equal to x in a scenario where I in fact observed x equals 0, writing that as x prime, and y equals 0. Right, so what's the question here? I observed the system and I saw that treatment was not given and the patient did not survive. I want to know counterfactually what would have been the probability, or what is the counterfactual probability of survival if we had instead, given the treatment. Okay, given an observation of what actually happened, what would have happened was the probability of an alternative given this. So how do we calculate this? Well, we have to calculate the joint probability of y sub x and x prime and y prime, right? Which involves an intervention of x and also a sort of null intervention, what actually happened. And so we have to compute that joint probability and then divide by the normalizing factor probability of x prime, y prime. Okay, so we have to essentially do this operation that we had on the previous slide. And if you work that out, you'll see that even though the patient didn't survive, if we had instead given treatment, still the probability of survival would have been 0.02. Okay, so does that make some sense of why this actually goes beyond even just asking about probability of y sub x? It's probabilities of y sub x in a scenario where we've made some observations. Intuitively, what's going on, when we make some observations, we have a posterior probability essentially over all the exogenous settings. And so we use that posterior probability to recompute y sub x, essentially. That's really all that's going on at an intuitive level. Does that make sense?
Yes.
Great. Okay, super. So now everything we've been doing so far is semantic. We have these models, and we said that these models now give rise to these different types of distributions. And so sometimes these three types of distributions are given these kind of intuitive meanings where, if I'm just asking about the probability of V in the observational setting, this is just passively observing the system and looking at the correlations among variables, essentially. It's a kind of observational distribution. Interventional allows us to ask what would happen in the system if I were to go in and change it. And then counterfactual allows us to ask about the probabilities of joint probabilities of different ways this might go. So essentially asking simultaneously, what's the probability that were I to do this, that would happen, and were I to do this, that would happen, right? Okay, so these are just quantities that are just implied by or defined by a structural causal model. And now I want to turn to a formal language for reasoning about these structures. So this is going to be a probability logical language given by Boolean combinations of comparisons between probability terms. And so T are going to be probability terms P of beta and possibly some further operations over these probability terms. And so this is where, well, there's two dimensions of variation that I want to consider here. There's a lot more you could explore than this, but I want to consider how much arithmetic do we admit over the probability terms, number one. And number two, which beta do we actually allow in these probability terms? So what are those beta? There's a lot more you can do here with probability logic, of course, and this is all essentially, propositional probability logics. You can consider, quantifiers over field terms, over these numerical terms. You can consider, as Dr. Speransky has done very interesting work on, you can consider quantification over events and other kinds of things. We're going to deal with something very small here, but enough to reason about these causal structures. And so I'll come back in a moment to the arithmetic question. I want to focus instead on the probability of the betas. So what betas are we going to allow? And so as far as arithmetic is concerned, let's just assume that we have this language that we allow polynomials over probability terms. So arbitrary polynomials, plus and times. Okay, then what are these probabilities of betas? This is going to give us a hierarchy of languages. So if we allow beta only to be propositional, and by that I mean Boolean combinations of variable settings, then we get a language that we're going to call L1. So we fix the arithmetical to be polynomials, and then we get L1 if we make beta propositional. L2 is, in L2 we're going to allow beta to be conditional formulas. So we'll write this in a dynamic logic way, probability of phi given an intervention of alpha. And finally, in L3, the most expressive of these languages, the largest language at least, we're going to allow beta to be a Boolean combination of conditionals. So this is essentially bringing us to counterfactuals, because this gives us a hierarchy of logical languages, L1, L2, L3. And these probability terms, just as before we kind of said that all these quantities are defined, this essentially just tells us exactly what the interpretation of each of these probability terms will be. Everything that I did in the first part is just now going to give us the formal semantics for for these probability terms, and then the rest of the language is totally determined. Booleans are Booleans, and comparisons are just comparisons of these numbers. And plus is plus and times is times over now real numbers in the unit interval. Okay. So one thing you might ask, immediate question you might ask, and this is going to be the central theme in the very end of the talk when we get to topology, but is this actually an increasing sequence of languages, expressively speaking, right? So we know the languages are getting bigger syntactically in the sense that we, add more complex probability terms as we go up from L1 to L2 to L3. But is this, properly speaking, an expressive increase? So I'll just show you some very simple examples demonstrating that it is. So here's the simplest model that we started with, which is these two fair coins, U1, U2, and then X takes on U1, Y takes on U2. We can calculate that it's kind of obvious that all of the settings of the variables are equally probable. They're all 1/4. So in L1, this is essentially describes the entire L1 theory of this model. It's kind of everything there is to know is that all the settings have probability for. Likewise, because there's no interesting causal influences here among the endogenous variables, the probability of y sub x is just the marginal probability of y. It's just a half. Okay, so here's a model. We just did some calculations. The question is maybe you can already see that this quantity, probability of y sub x being a half, was certainly not implied by the L1 facts. And in fact, we can keep all the L1 facts the same and get wildly different, or at least, wildly different interventional probabilities. So here's one model that has the same observational distribution. Again, all the settings of x and y are observationally, their probabilities are all the same, all fourth, but we've just changed the interventional probability where y now demonstrates a dependence on x can be pushed up to 3/4 in this case. Okay, so this is just to say we can keep all the L1 facts the same and change the L2 facts. So this is just to say causation is not implied by correlation. Kind of familiar idea. Maybe more interestingly, we can have L1 and L2 all the same in two models and nonetheless change L3 in dramatic ways. So here's an example with the same model. We just said probability of y sub x, same as probability of y, which is a half. But here's a counterfactual, which is maybe not surprising in this case. If I observe x is false and y is false, both equal to 0, then even if I were to go in and change x, it wouldn't change y. Y is still 0, right? So the counterfactual probability of y given an intervention of x in this setting where y and x are both 0 is 0. Okay, but we can now change this model to make it the same for all the interventional probabilities and all of the observational probabilities, but now flip this counterfactual from 0 to 1. So make it as extremely different as you like. Where now y depends on u2 still, but it depends on u2 and x. So y takes on the value 1 just in case x and u2 are the same, 0 otherwise. And so what you can check is all of the interventional probabilities are still the same. In particular, the probability of y given an intervention on x is still a half. But now you see that if I observe that x and y were both false, and then I go in and change x to be equal to 1, then because u2 must have equaled 1 as well, y will equal 1. Okay, so L1 between two structures can be the same but change L2. But you can also have L1 and L2 the same in two structures, and then you can toggle with L3. So this is genuinely an increasingly expressive sequence of languages. And this will be, I'll come back to this theme in a moment, after now saying something about the axiomatization and also the complexity of all of this. So So suppose we take L1. So because these are all different languages, they're, they are increasing in expressive power. It's interesting to consider their complexity and axiomatization separately. So L1 is essentially just a pure probability logic. It's a probability logic with polynomials over probability terms. And I just want to say something about the axiomatization of this, because somewhat surprisingly, this had never been axiomatized in the literature. And we've done this recently. So what do you get? Well, you get essentially, somewhat obvious probabilistic reasoning. So we have transitivity and comparability of this inequality. We have Boolean reasoning. We also have that if, beta, so everything here is propositional inside the probability operators, right? This is pure probability logic. So beta implies alpha as a matter of Boolean logic, then the probability of alpha has to be at least as great as the probability of beta. We have non-triviality. And then this last principle says that, essentially says additivity, that alpha is equal to the probability of alpha and beta plus the probability of alpha and not beta. That's an additivity principle. And then another thing that we've done here is just account for all the arithmetic in the following way. So, so we have, if we only had addition, this would actually be complete. This is a couple of simple rules for addition, it's associativity, commutativity, and zero. And then a couple of kind of cancellation type principles for addition. But if we have multiplication as well, we have to add a few more principles, which all are, again, quite straightforward. But then what we can do to show completeness of this polynomial calculus is to essentially invoke a known result of solutions for semi-algebraic systems. So this is the so-called Positivstellensatz of Stengel and Criterion. And we essentially show that especially this last axiom here, for products and sums combined, allows us to essentially turn that solution theorem, the Positivstellensatz, into a completeness theorem. So we have all this arithmetic, and then we have the probability axioms, and that gives completeness. Okay, so I can say more about this, but that's L1. Nothing causal here. This is just pure probability with arbitrary polynomials, and because these are kind of real polynomials, we have Positivstellensatz as the relevant solution concept. Okay, I should say in the additive case, we don't have to do anything like that. We can do pure variable elimination argument to get completeness, so things are even simpler there. Okay, I'm going to.
Could you tell us what is this Positivstellensatz?
Yeah, Positivstellensatz gives it's sort of by analogy with Nullstellensatz. It's for semi-algebraic systems. So if I have some set of strict so non-equalities and inequalities and equalities over the real polynomials, essentially, this gives us exact conditions under which there's a solution to that set of constraints. And the technical details get a little bit complicated. It's about, this is related to sums of squares and this kind of stuff that that people have been interested in. And I can say more, but that's basically what the result is. And so we essentially turn that into a proof system in this language. People have turned that into proof systems in bigger languages. Essentially this is some kind of computational geometry, because we're dealing with a lot of these things come up in any case where you need to solve systems of real polynomials. But we have a somewhat restricted language here with just these essentially propositional components, and hence that's the work is just essentially translating that into this calculus.
Okay.
Okay, so that's pure probability logic, nothing causal at all there. I'm going to skip L2, mostly because it's a little bit idiosyncratic. It can be axiomatized, but it's somewhat idiosyncratic because you have this syntactic restriction where you can only talk about probabilities of conditionals. You can't talk about probabilities of Boolean combinations of conditionals. So what's going on with L3? This is the largest system, essentially. This is the system where alpha and beta can be arbitrary combinations of conditionals. Well, we have one change to the probability axiom, which says that we need to ask not just when beta implies alpha as a matter of Boolean logic, but also as a matter of conditional logic in the system that I presented before. So if this is sort of a valid implication involving these conditionals, then the probability of alpha has to be at least as great as the probability of beta. And one more change to the pure probability calculus is that there's this kind of interaction between probability and the conditionals, aside from the one I just mentioned, which is the following. We said that, that if we have these, you can't have any cycles of dependence. And now we have essentially a probabilistic version of that, where I have the probability of xi causally impacting xi plus 1. If that's positive, then getting to the final pair, k can't also impact 1 with positive probability. So we have essentially a probabilistic version of this acyclicity axiom, and that completely axiomatizes the polynomial calculus with these causal conditionals. Okay, so these are the completeness results. And I want to say something about complexity, because we have, and now I also want to come back to the question of how much arithmetic we're actually going to admit. I just presented the setting where we admit all the arithmetic we like, essentially, plus and times arbitrary polynomials. But we have now essentially a two-dimensional space. One is how much arithmetic, two is how much causality. And you can ask about the complexity of the various satisfiability problems across this space. And restricting attention now just to the probability calculus. So we're talking about L1, and just asking the question, how much arithmetic do we allow? What we see, and this is very recent work, just of the last month or so, what we see is actually a kind of bifurcation. I've mentioned 4 systems here, 4 canonical systems, but we've studied a lot more than this. So this is, on the top right is the one I presented, the polynomial calculus, sat for that. And this again is pure probability. On the bottom left is comparisons. So we allow no arithmetic over the terms whatsoever. It's just pure comparisons. On the bottom right is the additive case, the linear case. And on the top left, I didn't mention this explicitly, but you could have conditional comparisons. So comparisons of conditional probabilities. And what we see is just a complete bifurcation. So everything falls under in one of these two classes. So anything that's purely additive, we actually know this is older results going back to 1990. Everything there falls into NP. So all these probability logics that involve only addition side of NP. So the new discovery that we've been surprised about is that any modicum of multiplication leads to this complexity class ETR. So what is ETR? ETR is the complexity. Well, so what are we dealing with? We're dealing with real polynomials, and we know from Tarski that the first order, the elementary theory of real numbers is decidable. But you can also consider just the pure existential fragment of real arithmetic, and that is also, of course, decidable. It's also known to be in p-space, and it's given its own complexity class, ETR. It's written here, yeah, ER, existential theory of the reals. And all that's known about that complexity class is that it's in between NP and p-space. So that's a sort of major open problem in complexity. What exactly is this ETR class? But what we see is that all of these probability calculi, including even very simple probability calculi that only allow qualitative comparisons between conditional probabilities, all side with ETR. They're all ETR complete. And in fact, we found very small, like even just reasoning about probabilistic dependence, very qualitative kind of thing with probability equalities, even that's ETR complete. All of these very simple systems, if there's any multiplication we can do whatsoever, that brings us to ETR. So there's this kind of bifurcation in these probability logics. And so that's all for pure probability logic. What happens with causality? So what if we add in all of these causal, essentially we're embedding a modal system within a modal system in some sense, where probability logic is one modality, and then these conditionals are another modality. What happens to the complexity? So the answer is actually nothing. We can just show totally systematically, anytime I have a causal query, even in the largest language L3, I can systematically reduce that to a pure probabilistic query in any of these languages, no matter how much arithmetic we start with. So even the pure qualitative case, all the way up to the polynomial case, we always have this reduction. So, so complexity, it's really about how much arithmetic we have, and it's really about how much, whether we have any multiplication at all, anything that can essentially smuggle in some multiplication, and everything in any case remains within ETR. Okay, so that's complexity. And this is probably a good time for a break. I haven't gotten to any of the topology yet, but how am I doing on time? Maybe I'm not doing too well on time. I'm not sure.
Well, our time restrictions are not that strict.
Okay.
So in principle, our talks are normally something like 1 hour and a half.
Okay.
Plus discussion. So this is.
Okay, maybe I should pause here. Then it's ask if there are any discussions, any points of discussion or questions or clarification or objections or anything. Because
so what are the known bounds for this ETR class? Is it at least exponential or something?
No, it's all that's known is that it's in between NP and P space.
Ah, okay.
So the existential theory of the reals, there's this result by Canny that ETR is in P space, and it's certainly as hard as in P, and that's, to my knowledge, all that's known about it.
Mm-hmm.
Well, a lot more is known about it, of course. There's lots of complete problems for it. We've just identified a few more. It's closed under NP reductions. Lots is known about it, but as far as its relationship to major, I mean, in some ways, it's kind of like the real analog to NP, right? If I consider like integer programming, like a bunch of polynomial inequalities where the solutions have to be over integers, that's a kind of classic NP kind of problem. And now if I consider it over real numbers, that's ETR. So it's really close to NP in some sense, but of course, the underlying algebraic structure is different. So there's a bunch of problems in, as I mentioned, computational geometry, actually, that are complete for this class. Questions about Nash equilibria in games and all kinds of other things, and computer vision and other kinds of things. But here, probability logic and also causal probability logic are just more examples.
Mm-hmm.
Good. Okay, so maybe if there's no other questions or comments or anything, I'll move on to the topology part. So I mentioned this, this sort of setting at the very beginning. In causal inference, we're often interested in, if I have some assumptions that I'm willing to make, I have some data, when can I reach causal conclusions? And now, what we've done by introducing these logical languages is that we can essentially formalize each of these components as in our formal languages. And so a lot of questions that you'll find in the causal literature have the following kind of shape. Suppose I have Li assumptions for I equals 1 or 2, and I have Li data. So I have assumptions that I can formulate at some level, and I also have data that either come from passive observation or from experimentations that might be L2 data. When can I actually draw more substantive conclusions? So I want to draw a causal conclusion, for instance, from observational data, or I want to draw an explanatory conclusion involving counterfactuals from experimental data. Okay, those are the kinds of questions that we often want to be able to ask. And now we can just turn these questions into actual logical entailment questions, right? And here's a first result that we have from last year. This is with Elias Barenboim and Juan Correa. I should say all of this is joint work with my PhD student in computer science, Delager Eubling. But this says that L1 facts, so L1 never determines L2. That is to say, if I have a model and I consider all the probabilistic statements true of it, that never determines all of the L2 facts. So there will always be a model that differs on the L2 facts. So the example I gave you was, not just the rule, it's universal, that always happens. So of course, correlation doesn't imply causation. But we might ask about the case of 2 to 3, and that case turns out to be a little bit more subtle. So let's introduce a sequence of spaces. We're going to topologize these, but let's consider a sequence of spaces. So we have the space of all models. And let's now kind of coarsen that in a sequence of 3 coarsenings. First, let's let S3 be the space of all L3 theories. So we basically are collapsing models when they agree on all the counterfactual statements. Okay, and then let's do some further collapsing, potentially, where we now just consider the space of all L2 theories. So now we're collapsing any 2 that agree on L2. And finally, let's do the same for observational, for L1. Okay, so this gives us a sequence of increasingly coarse, coarse versions of my original space of models. Okay, here's a question you might ask. Consider S3. So, what we said just before was that, when I go from S2 to S1, that's a genuine coarsening. That's sincere. That's a big coarsening. Right, but what about S3 to S2? So what we saw in the example I gave some moments ago was that I could have, for instance, the blue here, I could have 2 models that are different at S3, but agree on their S2, or are the same at L2. Sorry, so I have sort of 2 S3 objects, 2 L3 theories that project down to the very same L2 theory. That can certainly happen. But in causal inference, we might be interested in this gray area. The gray area down here in S2, those are the models or theories in which knowing all the L2 facts fixes all the L3 facts. Okay, so this is the sort of injective fiber, right, of this projection. So I have merely knowing all of the experimental quantities, essentially. If I were to do all the experiments in the world to convince myself of the probability of Y given an intervention on X and all the other experiments, then I'd also be able to answer uniquely all of the L3 questions, all the counterfactual questions. Okay, so that's this gray space subspace of S2. So the question here, and this is the question that's empirically relevant, is how large is this gray area? Okay, so how big is it? And should we expect ever to be essentially in that gray area where knowing all the L2 facts? We know knowing the L1 facts doesn't determine the L2 facts. But what about L2 to L3? Does knowing the L2 facts tell us a lot about the L3 facts? And one way we've answered this question in the previous work that I just mentioned with Elias Barenboim and Juan Correa is doing a sort of measure theoretic study of this, where we put a measure on the space of essentially L3 theories, and we show that the gray space has measure 0. So there's a previous result that we have that says that this is small in a measure theoretic sense, but for various reasons that we can talk about, and I'll try to go through this quickly because I know that I've taken already a lot of time. We want to ask this not in a measure theoretic sense, but in a topological sense. So what's the topological analog of small measure 0? It's meager. So the question is, can we understand this set in topological terms? And what is the natural topology? This is even more important. What's the natural topology to put on these spaces? Okay, so what I'll do now is just say, what is this topology? What is its empirical significance? And then at least state the results. Okay, so here's the topology. And again, consider just the space of probability measures on counter space, say. So this is just the probability measures that we get from basic probability logic. The topology is called the weak topology, where we say a sequence of probability measures, Pn, converges weakly to another probability measure, P, if for every clopin, the probability of that clopin converges to, has probability of beta as a limit. Okay, and now we just use this convergence notion to define the topology, where we say the closed sets are the ones that contain their limit points. Okay, so this is a function space, right? This is a topology on a space of functions, and it's defined in the following way. There's much more general ways to define this connected to functional analysis and everything, but for our purposes, this is all we actually need to work with. And there's an intuitive way of thinking about this that has a little bit similar flavor to interval topologies and so on. A subbasis is given by sets of probability measures where we fix a clopin beta and a real number r, a rational number r, and we just take the set of all the measures that give beta greater than probability r. Okay, so this is a subbasis that close under complements and finite intersections, you get a basis, get a topology. Okay, so this is the so-called weak topology. And before talking about this topology on the causal spaces on S2 and S3, let me just say why we adopt this topology. And this is a recent idea that connects it with learning theory. Okay, so imagine we're in a setting where we have some some scientist or some data scientist who's going to be receiving observations. So essentially getting information about this, some underlying probability distribution, some underlying data generating process. And we're getting increasing data, theta 1, 2, 3, essentially longer and longer data sequences. And we can talk about the notion of a test, which is basically a claim of acceptance or rejection. And we're thinking of this in a kind of statistical setting, a sort of frequentist statistical setting where we want to reject some null hypothesis. Okay, so at each stage of inquiry, this data scientist is either accepting or rejecting a null hypothesis. Okay, and then we say that some set of measures, some set H of measures, property of measures, is verifiable if, and this is a somewhat complicated definition, but let me just say it in words, if there's some epsilon and a sequence of tests, for each number of data points, such that number 2 here, in the limit, we reject the null hypothesis with probability 1. Okay, so if P is actually in the set of the set H, then we reject with probability 1. And otherwise, if P is not in the hypothesis, then at no finite stage do we actually have probability of error greater than epsilon. Okay, so it's a kind of bound on the error that we can have in doing a sort of a null hypothesis test kind of operation on this sequence of data points. Okay, so that's what it is for a hypothesis to be verifiable. And here's the results. It maybe even looks plausible the way we've set it up. And this is from Konstantin Genin and Kevin Kelly, which says that a set of hypotheses is verifiable in this sense, if and only if it's open in the weak topology. So I hope the intuition for this is somewhat clear. For instance, suppose we just have a coin. Then the claim that the coin is biased, for instance, not equal to 0.5 is open. Whereas, the claim that the coin is fair is closed, and those are going to be verifiable and not verifiable in that case, respectively. Okay, so this is the kind of thing that in the limit of infinite data, you can, be sure that you're in that hypothesis space, or that is you're in that hypothesis, you're rejecting with probability 1, and otherwise you can't actually bound the error. Okay. So that's the link to learning theory. which is what also we might want to ask questions about in the causal setting. So we can extend this weak topology across to each of these spaces. So in S1, it's just what I presented as the weak topology. What is it on S2? Well, on S2, essentially, what do we have? S2 looks like, we have a probability for each conditional, which if I consider an intervention, that essentially gives me a kind of experimental setting. And now I'm going to take the probability for each of those experimental settings and now take the infinite product across all interventions. Okay, so this gives me a product topology of each of these weak topologies. And finally, at S3, we can actually understand these probabilities of conditionals, Boolean combinations of conditionals themselves as probability distributions, and we can actually put the weak topology on those joint probabilities. Joint probability distributions in exactly the same way as I presented before, just with a richer probability space. Okay, and so here's a theorem: is that result from Gannon and Kelly extends to, for instance, S2, where we can define a notion of being experimentally verifiable, not verifiable from passive observations, but verifiable from experimental manipulations, where I can do as many experiments as I want and take that to the limit. Then a hypothesis experimentally verifiable, just in case, is open in this S2 topology, in the product of weak topologies. Okay, so the kind of empirical significance of this continues up this causal hierarchy. Okay, so what do we have? We have this space M of all causal models, and then we project down to a coarsening S3, and then we take further projections down to S2 and S1, and it turns out these pi2 and pi1 are actually continuous in these topologies, and so you get a nice little kind of topological hierarchy there. And you probably see where this is going now. We now can ask the question, what's the status of this gray area, of this collapse set? These cases where experiments allow me to answer arbitrary counterfactual questions. And the result is that this collapse set is meager in the topology on S2. And what is meager? So remember, a nowhere dense set is one where any open set contains an open avoiding that set, and then a meager set is a union of nowhere dense sets. And so intuitively, these sets are sort of small, topologically speaking. They're the ones that are approximated by sets that are punctured with holes, essentially. So they're kind of not very robust in this space. And so the collapse set is small in S2, and in fact, meagerness gets reflected back by continuous maps. So its pre-image is also meager in the weak topology on S3. And so we also have an analog up in S3. So this is to say that, well, if we put this together with the conceptual interpretation given by that learning theoretic result, then the corollary is that any assumptions that would allow us to infer counterfactual probabilities from experimental data must themselves be statistically unverifiable assumptions. So if we want to make assumptions that allow us to infer counterfactuals from experimental data, we essentially have to make assumptions that we couldn't even verify in principle from experimental data in the limit. Okay, so sort of causal assumptions to make causal conclusions are necessary, essentially, is what this says. And I'll just mention here at the very end that we can actually witness this with any number of different counterfactual queries. So I stated the result in a somewhat blunt way, but we can actually sharpen it to say that any of these quantities are underdetermined in a co-meager set. Okay, so I can talk more about that, but these are the kinds of things that come up in practice. We mentioned probability of sufficiency a few times in the examples, but there's lots of other quantities that people are interested in evaluating. Okay, so just returning to this this last the diagram that I pointed out at the beginning. This is essentially the problem of causal inference, is understanding sets of assumptions and types of data that allow you to conclude, causal answers to causal questions, which could be anything from, precise evaluations of some causal query to bounds to whatever you like. This is, essentially the problem of causal inference. And what I hope to have convinced you of is that this can be seen through a logical lens in a helpful way. And it can be helpful for conceptual clarification for causal inference, but it also gives us a whole lot of new kind of problems for logic. And so thanks for your attention. And here are a couple of references from some of the work that I mentioned there. So sorry I've gone on for so long also.
Thank you very much for an interesting talk. Okay, I'm sure some participants of the seminar will have questions. So, I have one, but well, more than one, but I think somebody.
May I?
Yes.
I didn't quite understand what exactly goes into the space. I mean, do you fix X, U, and F and only vary P, or?
Great question. Yeah, great question. What goes into the space? Yeah, good. So notice I didn't topologize in the space of the causal models. And what we do, in fact, we even did this in the measure theoretic version of this, is we essentially get rid of what you might call sort of intentional details. So all of those P's and U's and everything, as I mentioned at the very beginning, we're not usually interacting with those at all. So we're essentially sort of getting rid of them, essentially. We're considering these as, we're coarsening them so that we don't pay attention to, essentially we're saying that, if I have two variables instead of one, U1, for instance, it makes no difference because it's not going to make any difference in how we're, in any of the queries we want to be able to make. So we've essentially coarsened to collapse any two causal models that imply all of the same counterfactual probabilities. So all of those intentional details get abstracted away from. You could, and we did do this in the previous work as well, you could put, we didn't topologize it, but we did put measures on those objects with all of their intentional details, and that can be interesting too. But from this perspective, we wanted to keep things tethered to the logical languages that are only dealing with the endogenous variables. And so what we get is all the patterns that you could get from any SCM, any structural causal model. But we want to abstract away from all of that messy detail.
Okay, Stanislav, you had some questions.
Yes, I have just two very small clarificatory questions. The language L1 you mentioned, is it exactly the language of polynomial weighted formulas from Fagin, Halpin, and Megiddo, right?
It's pretty similar. It's very similar. It's not exactly the same because we do not have rational constants or integer constants, but it is very similar to what they had. And you might remember they didn't axiomatize their language.
Yes, I mean, the reason why I'm asking is because there is no axiomatization for that.
That's right.
I mean, you can easily get that if you add quantifiers over real numbers, but that's cheating, of course. I mean,
that's right.
That's
right. Yeah.
Okay, right.
So I should say also, though, I should just say as a sort of side note there is work, and you probably know it, but just for others, there is work that has given an axiomatization of that language that's again with real terms. This is by the probability logic group in Belgrade, where they actually have an infinitary system that is sound and strongly complete. So I should mention that this is a finitary axiomatization,
yeah, sure,
so it's sort of distinctive in that way.
And another question is, So suppose that you have only linear combinations of conditional probabilities now, right?
Yeah, good, yeah.
Is it true that the complexity is still ETR?
It's worse than that. Actually, we don't even have to allow linear combinations of conditional probabilities. Comparative conditional probabilities. It's
Okay.
already ETR complete.
Okay.
And so,
So
also
you don't need arbitrary polynomials.
It is stronger than the left top corner of your diagram or something like
that's
that.
right. That's right. Yeah, it's the top left corner. Exactly. Yeah.
Because I mean,
it's bizarre. I was not expecting that, to be honest.
Okay. Because I mean, their original motivation for introducing polynomials was that because we want to reason about conditional probabilities. That's pretty much it. I mean,
exactly.
That's how. So these are like degree 2 polynomials or something like that. So
that's right. That's right. That's exactly right.
Okay. Thank you.
Isn't that weird? I mean, I agree. I mean, that was the motivation for not just Fagan and colleagues, but also others who have followed up on that work. And we kind of feel that you might as well throw in arbitrary polynomials, which are really nicely behaved, and they're easy to reason with and everything. And the complexity is no higher. So it's even worse. Even if you just throw in not even conditional independence or dependence, but just unconditional dependence. If you just have unconditional dependence, so X depends on Y, not independent of Y, or dependent of, doesn't matter, it's closed under Booleans, or even if you don't close under Booleans, actually. And then you allow probabilistic equalities, even that's ETR hard. So I really mean like any amount of multiplication, binary multiplication, that's not even full multiplication like you have with conditional probability.
Well, that's interesting because I mean, in my paper where I said that if you have quantifiers over events over this polynomial quantity-free language, and then the complexity goes up to complete second-order arithmetic. You can also do that if you have something like binary multiplication.
Interesting. Yeah, right.
So that's pretty much everything you need to encode full monadic second-order arithmetic, and I mean non-monadic also.
Maybe this sounds like there's something general.
It's barely mentioned there. I mean, I haven't provided a proof, but yes, you can do that. So that's pretty much interesting. Okay, we can go back to that at some point.
Yeah, of course. That's fascinating. Now it makes me wonder whether there's something much more general going on here. That's happening both at this low complexity level, but also at that high, going all the way to. That's fascinating. Thank you.
Yeah. So I had questions of several kinds, but let's say the first one would perhaps be I would like to see more examples of reasoning using these logic. So somehow one thing is to let's see, have this notion of model and and see it. But the other thing is some concrete examples of what can you, is it really about reasoning so you can make conclusions using this?
Good. Yeah, that's a great question. The results that I've presented, I haven't presented anything that goes really in that direction. On the one hand, we have this just abstract, completeness and complexity. And then the main result that I presented today was this causal hierarchy theorem, which is definitely not about concrete using a really abstracting way in a big way. But I guess the way I think of it is we have this big negative result, right? That says that without strong assumptions, you won't get any of the conclusions you want. But now all the action in causal inference is usually about positive results. So if I give myself some types of assumptions, and then I assume that I'm going to get some kind of data, I actually now want to know that I can churn out some consequences, right? I can actually get some causal conclusions. And this is definitely where you can actually see instances of reasoning. So I have I added some slides just in case anyone was going to ask about sort of more positive projects, just to show what this might look like. I don't know if that would be helpful, shall I maybe just show you? Okay, so let's see, let me share again then. I will not show you any derivations because wouldn't
That
even
would
fit
be
them on the slides.
too unreadable, perhaps.
Yeah, but just to show you what kind of thing you might want to be able to derive. So let's see, is this, let me make it full screen again. So what are the, I should just say, like, what are the kinds of assumptions that people want to make? So if I go back to this picture, so the data are going to be either, either pure probability statements, or they're going to be probabilities of conditionals, these potential outcomes that you get from experiments, ideal experiments. What goes into the assumptions? So this is where different schools of thought in causal inference differ in what kinds of assumptions they find most natural and good to work with. And one big group of researchers is interested in graphical assumptions. So I kind of hinted at this whenever I drew these graphs, right? The sort of graphs of dependence among variables. And if you can make certain assumptions about dependence and independence, that is presence or absence of certain links in this graph, this populates our set of assumptions in a really nice and elegant kind of way. So none of this is our work, but our work can formalize what people do here. So here's an example. Suppose we take this medical scenario again, just the same example that we had throughout. Here's the graph. Y depends on X depends on Z, and there's all these exogenous sources of variation. Here's a type of graph that people are interested in, which is actually a graphical coarsening of this graph, where I don't know anything necessarily about the exogenous variables, but suppose I know, well, let's rewrite this as follows. I know that Y depends on X, and X depends on Z, and also there's a confounding variable of Y and Z. Okay, so that's true of this situation. And suppose we have some domain expert that tells us, yeah, our scenario is like this, right? A classic example is that this Z is like smoking, Y is cancer, and X is tar in the lungs. So maybe smoking causes cancer via this intermediate variable of tar in the lungs, but then there's all these sources of variation that impact both likelihood of cancer, but also likelihood of smoking, that confound those two variables. If we have a scenario like this, then there's this theorem. This is so-called front door criterion, which is that this equality is guaranteed to hold. The probability of Y given due Z, so if I intervened on Z, then this actually amounts to an arithmetical formula involving only observational probabilities. So the beautiful thing here from this front door criterion is I can actually estimate this interventional probability from these observational probabilities. This is the right-hand side is just implied by the joint probability, right? Just a bunch of conditionals and sums and products. What we can do is actually derive this equality from some assumptions that come from this graphical set of assumptions. And this involves a so-called do calculus from Yuda Pearl, which essentially link, and I won't go through these in detail, but these link graphical properties. So the if statements here are graphical properties. This is not probabilistic independence. This is a graph theoretic notion called d-separation. If in this particular graph that I manipulated in a particular way, these variables satisfy this graphical property, then this formula, essentially, I didn't write it this way, but this is a formula in our language holds. So there's this correspondence between equalities of probability terms involving conditionals and graphical properties. So here's what we can do is actually write down all of these assumptions applied by the graph as assumptions, and then just use our calculus to derive this equality. Okay, and you can actually, and in some paper, we actually have that derivation using the axioms that I presented, but that's one example. But in order for this to become interesting, that is, interesting from the perspective of causal inference, we need some source for further assumptions. And here's one source for further assumptions, which is sort of qualitative graphical properties that via this do calculus issue in probability statements that are then in our language. So that's where derivations actually come up and where we can give them. and that's the systems are complete. So actually anything that follows from some assumptions, there will be a derivation. So does that give some flavor, I guess, of what this looks like in a concrete case? I didn't give you the derivation, but the derivation is essentially this equality statement.
The formula, yes.
Yeah, a formula from a whole bunch of other formulas. Yeah.
Yeah, in fact, if you have a complete system of, let's say, axioms for your logic of causal inference of that, or of one or another language, that can be, well, it seems that, well, I'm thinking about, real world applications of this. Probably you know better how to sell it, but what do you think about the following? So you suppose you are building some medical expert system or some other expert system, and you need to produce not only the the number stating some probability of something that of some event that will happen, but also some reasoning for the doctor to see why the expert system. So it's like, how do you call it? Artificial intelligence.
Oh yeah, expert systems and that kind of thing.
There is this, like in machine learning, you don't know the causes. Why?
Oh yeah, all the explainability, interpretability.
Explainability, yes,
Yeah,
indeed. So your logic provides some kind of explainability for such conclusions. So if you have a proof, if it is short, maybe it can serve as a kind of explanation.
Yeah, I love that actually, and I mean I would like to be able to claim some originality for that, but it turns out people are actually already doing something like this in restricted settings. So we gave a totally complete, totally general completeness proof, but people actually have they're not formalized in proof calculi, but well, effectively they, I guess, are in some way. So people have restricted versions of completeness theorems actually. So this do calculus that I just mentioned has been shown complete for estimation of a particular type of query. In fact, a whole bunch of a range of these types of results. And then people have actually implemented algorithms for determining whether a query is identifiable from some types of data. And there's a new tool out called Causal Fusion by one of my collaborators in all this work, who's a honest to goodness causal researcher who actually does applied type of work as well, Elias Barenboim, called Causal Fusion. And it actually does exactly what you're suggesting. It actually gives essentially a derivation of the, of either the, well, in the case that it's identifiable, of the derivation of what makes it identifiable. And it's a beautiful kind of tool. It's of course limited in the sense that it doesn't encompass all possible causal queries like the calculus here does, and the fact that this is ETR hard in the general case might make it so that you might not hope for a simple complete algorithm like that. But I think it's this is just to say it's a very good idea, and such a good idea that people have started doing it very recently. So I don't know how much, honestly. I'd like to be able to say that this work has direct practical import, but I do think of it as largely a theoretical exercise, and conceptual exercise.
Of course. No, that's clear. That's clear. But on the other hand, I think that practical interest towards such things is growing somehow.
I think you're right.
That engineers would actually be interested in seeing some such applications. I don't know.
Yeah, I appreciate that.
Yeah, but also conceptually, I also wanted.
Yeah, of course.
Well, my questions, remaining questions are really global questions. So somehow before the most global question asked less global question. So in quantum mechanics, there is issue of causality, etc. is quite also an interesting one. So I wonder how much similar formalisms have appeared there?
Yeah, this is a big topic, especially recently, interestingly. So, you know, the history of connections between causality and physics more broadly is fraught. If you know this, there's this famous quotation that people often mention by Bertrand Russell, that I forgot exactly how it goes, but it basically says that causality, the very word, should be banished from science. In fact, not just physics, but science altogether. Right? And this was a kind of dominant view in science and philosophy for many years. Recently, the topic has really you know, come back up. Of course, you know, there's all the EPR experiments about, you know, all of this stuff was definitely, causality was relevant there. But recently, there's been a lot of debate about how we should understand, specifically now that causality has been sort of mathematized. It had not been mathematized by any means at the turn of the century, last century. But now that we have a kind of mathematical framework, how does it fit together with physical theory? And that's a big topic that is, you know, outside my domain of expertise, but is very interesting. One thing I will say is that there's a nice kind of perspective on this from a causal researcher named Shulkopf, who's also just more machine learning researcher who does a lot in causality, who thinks of it in the following way. You have very low-level systems, which could be described by, you know, differential equations, the kinds of things that we describe in kind of physical terms. And then you have high-level systems, sort of just statistical models that capture, you know, in some high-level like regularities and correlations. And essentially what one way to understand these mathematical causal models is sitting somewhere in between those two. So they're not sort of purely correlational statistical information about macroscopic phenomena, but they're also not capturing all of the low-level physical details. They're kind of capturing some invariances that are implied by those low-level physical details and essentially reifying them into a formalism. So, you know, we can maybe understand these as you know, sitting somewhere in between these two extremes, capturing some of the real physics of it, whether we should understand that ultimate physics in causal terms or not. You know, it's very high level, just, you know, stuff correlating with other stuff. And a lot of the work that I do is, you know, cognitive science. And here I'm primarily interested in not, you know, the ultimate nature of the universe, but just how we conceive of it and how we conceptualize it. And there, these causal models are just construed as essentially intuitive theories of the world and how it works. And so then we really don't have to get into some of those you know, questions about quantum physics and that kind of thing. So there's different answers. It's a fairly flexible mathematical formalism. And you can ask the question about how, you can imagine what the physics questions, what physics questions come up, not just, you know, action at a distance, but also time reversibility and all that kind of stuff comes up there. There's direction of time, causality, and all that kind of thing. So those are all fascinating questions, but you know, the mathematics can be used for different settings with slightly different interpretations.
Okay. Good. Any other questions?
Just one down-to-earth question. The intervention operators commuting with negation is sort of something unusual for me. Would you think of some traditional modological context when such things happen?
Oh yeah, good question. What's another example where you just completely, yeah, because even in these sort of dynamic logics where it goes inside the modalities are formulas, so they're sort of model changing operations, even those don't, you know, fully commute, right? It's a good question. What is another example like that?
Yeah, it is kind of I wouldn't call it complete trivialization of model logic, but it significantly trivializes what's the content of the usual.
algebraically, it means that you have some Boolean algebra homomorphisms, right? Essentially.
True,
So-
true, yeah. Yeah, to my knowledge, no one has looked at the algebra of, just consider that deterministic setting, right? Just that conditional logic. No one's considered the algebra of those. But of course, it's this thing that happens where it's not just like a modal operator that you can consider as an operator on the Boolean algebra, but it's itself like a labeled, you have one for each. It interacts with the language in this crucial way. And that's maybe most apparent by the fact that, upon intervention of alpha, you have alpha. So that'd be fascinating just to know what kind of operator or family of operators that is algebraically. And to my knowledge, no one has looked at this. Yeah, I agree though. It's odd, right? that it just can use negations. So therefore, what it means is just that you can boil everything down to intervention literal Boolean combinations of those, because it's just completely, you can pull out any connectives at all. So maybe that's as it should be. So actually, sometimes when we do this work, we don't even write it as a modal operator. We write it variable subscript alpha, just to really capitalize on this fact.
Okay, good. Thank you for this talk and interesting discussion.